Go.
Hello, Dr. Sawtelle and ULAs of LB274. This is our group's formal lab on the Plato circuit. So in introduction, the goal of this formal lab was to create a working circuit that contains an LED bulb in parallel with the electric motor and a Plato resistor. The research question we had in mind was how to use the known resistivity of Plato to calculate the resistance of a handmade Plato resistor. And our predicted resistance of the Plato resistor was 3.864 ohms, and our actual measured resistance of the resistor was 1.8 ohms. So some important ideas and equations to consider in this formal lab was Ohm's law. Current through a conductor is proportional to the voltage across the conductor given by the equation V equals IR. The concept of resistivity, which is a measurement of the power of a material to resist the flow of electric current, and Kirchhoff's laws. So, current going into a junction equaling the net current flowing out of the junction, and the voltage rule, where the sum of all potential differences around any closed loop must be equal to 0. So in order to proceed with the formal lab, in our pre-lab, we had to calculate the resistivity of Plato itself. So we created a sample resistor made of Plato with various lengths, but keeping cross-sectional area the same. And using these values, averaging them out, we got to a resistivity of 0.023 ohm meters. So then we use this value when we're proceeding calculating the resistance of our caret resistor.
All right, so based on our instructions, we needed to make a circuit that was both with an LED bulb in parallel with an electric motor and a Plato resistor. In our experiment, we made our Plato resistor to look like a caret, and we had our motor fan on the left side in parallel with our resistor. We used 3 batteries, and this is what on the right side of our slide here is what our circuit looked like when we drew it out a little more clearly. So on the next slide, we have our caret resistor, and with some of its dimensions, we have a radius of 1 centimeter and a length of 4.5 centimeters. To predict the resistance of our caret resistor, we needed the radius, the length to find the cross-sectional area, and then we used the resistivity that we calculated from the pre-lab to solve for our resistance, plugging in 0.02697 ohm meters for this P, and then the length and the area to get 3.864 ohms.
For our results for the experiment, we used Ohm's law, and then we also looked at the voltage drop across the resistor, which was 3.6 volts, and the current across the caret resistor, which was 2.0 amps. And so then using Ohm's law, we were able to calculate the resistivity of our Plato resistor, which was found to be 1.8 ohms. And then in order to quantify our error, we calculated the percent error by taking the measured value, subtracting the actual value, and then dividing it by the actual value. Our measured value was 1.8 ohms, and then our actual value, which was predicted based on the pre-lab, was 3.684 ohms. And it was found to be 56%. So for assumptions we made and potential sources of error, because our resistor was a cone-like shape, we had to assume the area of the resistor stayed constant when selecting the radius, and so we just selected it from the middle, which was found to be 1 centimeter. And then for potential sources of error, there could also be the amount of Plato covering the copper wire, the amount of time that the Plato has been left out for, less voltage being the battery than advertised, or inconsistencies in the multimeter. And then another note is that in our current circuit, we struggled with the wire falling out of the Plato or not being tight enough within the resistor. So then we were having some inaccurate readings, but we just solved this by ensuring that there weren't any gaps or holes in our Plato. And then that is all we have. Thank you.